Welcome all in the lecture of the SAR polarimetry. Okay, so we have already gone through the lectures of the basic concepts of the SAR data processing 1 and SAR data processing 2. Okay, so we have learned about the basic concepts and how to process the raw data, basic concepts of raw data processing, and basic concepts of level 1 data processing. Means after level 1 is formed, which is the SLC data, so we can do the geometrical corrections and other corrections on the level 1 data. Now for the SAR applications, there are two terms. One is SAR polarimetry and SAR interferometry. So both this technique uses the SLC data. SLC data means it is using the phase information. Okay, so that actually in the level 2 data, most of the SAR products loses the phase information, only amplitude data is there. So we have to do, if our application is like analysis of the features and visual interpretation only, so we can use the level 2 data. But for the application of like SAR polarimetry and interferometry, we have to use the SLC data. Okay, so now we will go to the SAR polarimetry lecture. So earlier in the first lecture I have told you about the SAR image characteristics, in which the backscatter of SAR is depending on the sensor parameter and the target parameter. So sensor parameter is the wavelength, polarization, incident angle, and target parameters are the dielectric constant, surface roughness, moisture, and the local incident angle. So now we will go in deep on the polarization. What is how the polarization is affecting the SAR images. So what is the SAR polarimetry? Okay, so polarization refers to the orientation of the electric field vector with respect to the perpendicular to the direction of propagation. Okay, so we can see this is the basic propagation of the electromagnetic radiation. So in this, the electromagnetic radiation basically consists of the two parts. One is the electric field vector and second is the magnetic field vector. We will consider mostly the electric field vector, because the magnetic field vector we can derive through the Maxwell's equation. So if we know the how the electric field vector is oriented, so we will deal with the polarization concepts. Okay, so polarization basically deals with how the electric field vector is oriented with respect to the propagation of the wave. So this is the is the z-axis, is the propagation direction, and the blue is the vertical component of electric field vector, and the green is the horizontal component of electric field vector, and combination of this one will give the red. This is the resultant electric field vector. Okay, so in the SAR polarimetry, just we will see what is the polarization ellipse. Okay, so the path traced by the resultant electric field vector is called the polarization ellipse. So what I have told you, polarization is the orientation of the electric field vector. So what is the path is traced by this electric field vector? This red line is the electric field vector. How this resultant electric field vector is actually tracing the path? So this is called the actually the polarization ellipse. Okay, so this polarization ellipse has two things. One is the amplitude and the relative phase. If the components like this x and y components, that is called the horizontal component and the vertical component, are in phase. Okay, they are in phase. So we can say that is a linear polarization. Okay, basically in the SAR polarimetry, most of the SAR system have the linear polarimetry, means that H and V polarization are always in the phase. Okay, now how we define the horizontal and vertical polarization? Now this polarization ellipse is characterized by two angles. One is the orientation angle and one is the ellipticity angle. Okay, so what is the orientation angle? How this polarization ellipse is oriented with respect to the x-axis. Okay, so this is an ellipse, this is the major axis, this is a minor axis. How this major axis is making the angle with respect to the x-axis is given by the orientation angle. So this is the orientation. Second is the ellipticity. Ellipticity is the actually the angle which is varying from minus 45 to 45, and it will tell the degree to which the ellipse is oval and is described by the shape parameter which is called the eccentricity. And this angle is we can calculate through the formula tan inverse b by a. B is the semi major axis, semi minor axis, and a is the semi major axis. Okay, so these are the two angles. The variations of the two angle are that orientation angle is varies from 0 to 180 degree, and the ellipticity angle is varying from minus 45 to 45 degree. Okay, so if the orientation is 0, this polarization orientation means it is like this one in the x-axis direction, this is becoming 0, then we will have the linear polarization, and ellipticity angle is 0. Both in the case of horizontal and vertical linear polarization, this ellipticity angle is 0. So we are getting the linear polarization. When the orientation angle is 0, then we can get the horizontal. When the orientation angle is 90 degree, then we are getting the vertical linear polarization. So we can design our SAR system in such a way that we can have two polarization like horizontal and vertical polarization, and we can keep some phase in between them. Okay, so if there is a 0 phase, then there is a linear polarization, but if we are maintaining some phase like 90 degree, okay, so we can have a circular polarization. Okay, so we can make, by changing the phase between the horizontal and vertical polarization, the different type of polarization ellipse. If the phase difference is 90 degree, then we can have a circular polarization. Otherwise we have the elliptical polarization. Okay, and if the ellipticity is 0 and relative phase is 0, then we are having the linear polarization. Okay, so apart from normal linear polarization, which is also called full polarimetry, in our reset 1 and EOS SAR sensor has the hybrid polarimetry or the circular polarimetry. Means we can transmit the signal as circular and received as linear. Okay, so I will tell you later what is the hybrid polarimetry in detail. So this is the concept of the SAR polarimetry, polarization ellipse, where how we can make a linear polarization and how we can make a circular polarization. So we can say here in this case, if this is an electric field vector, then we can say this is the linear polarization. There is a simple line in the electric field vector is a resultant line. So you can see in the linear polarization, with the propagation of the wave, it is in the xy plane, it is making a simple line. But if we are changing the phase between the H and V polarization, so it is actually making the circular or ellipse shape polarization ellipse. Okay, so this is the polarization ellipse. It is a straight line in the linear polarization, and here it is circular, and here it is elliptical. So here the relative phase between the H and V is 90 degree. Here it is 90 degree. So any like 45 degree, it can make a elliptical polarization. So we can change this relative phase, and we can design our SAR antenna. So what are the polarimetry basics? So after interacting with the Earth surface, the polarization may be altered. Means if we are sending the SAR signal in some polarization, like we are sending at a horizontal polarization, that is a linear polarization, and we are sending the horizontal polarization. So when it interacts with the Earth surface, then the actually different features on the Earth will change the polarization. Means we are sending H, and it will change some polarization state of the SAR signal. So when the backscatter signal is we are receiving, so we can detect the change in the polarization. So either we can receive same as a H polarization, or we can receive as a V polarization. Okay, so we can in the linear polarization we can make a 4 combination like HH means transmit H, receive H, VV, transmit V and receive V, HV, transmit H and receive V, and VH, transmit V and receive H. So this is the basic principle of the polarimetry. Means if we are sending any signal, SAR signal with some polarization, then any Earth surface will change its polarization, and the study of these changes in the polarization is the SAR polarimetry. Okay, so how many what are the system we can make? We can make a single pole system, we can make a dual pole system, and we can make a quad pole system. Single pole means either we can make HH or VV, VH and HV. In the dual pole we have the 2 images like either HH plus HV or VV plus VH. We have the 2 images. In the quad pole we have the 4 images like HH, HV, VH and VV. So this quad pole is the full polarimetry system, means we are sending H and receiving V. So we have the more information because we have 4 images, and with the help of these 4 images we can deduce the orientation of different targets on the Earth surface. So what is the basic principle of SAR polarimetry? When the radar wave interacts with the surface and is scattered from it, the polarization can be modified depending on the properties of the surface. This modification affects the way the scene appears in the polarimetric radar imagery, and the type of surface can often be deduced from the image. Okay, so this modification what is happening in the polarization is studied under the SAR polarimetry. So vertically polarized waves interact with vertical structure vegetation, and horizontally polarized waves have greater interaction with the horizontal features like soil, road and river beds. And the cross polarization, like we are sending H and receiving V, are sensitive to the vegetation. So why but it is sensitive to vegetation, I will explain in the subsequent slides. So basically we can have the 4 combination. One is the HH, HV, VH and VV. Okay, so we can in the HH we are transmitting the horizontal polarization and receiving the horizontal. HV we are transmitting the horizontal and receiving the vertical, and VH we are transmitting the vertical and receiving the horizontal, and VV we are transmitting the vertical and receiving the vertical. Okay, so when we are transmitting H and receive H, that is called the copole. Okay, and VV are copole. HH and VV are polarized signal or copolarized images. They are usually strong, specular and surface scattering will happen. Okay, and cross polarized signal are means we are sending H and receiving V, means it is a cross polarized. So that is actually associated with the volume scattering. So I will tell you what is the volume scattering. A strong relationship with orientation of scatterers. Okay, because of the strong relationship with the geometry, the polarized signal usually depends on the incidence angle. Okay, so the polarimetry basically depends on the how the target is oriented. Means if we are sending H and it will alter the polarization state, means in the orientation is not in the horizontal direction, so it will change the polarization state of the signal, and we can deduce the orientation of the any feature in the Earth surface. So we have the 4 type of SAR polarimetry system like single pole, dual pole, quad pole or fully polarimetric, and hybrid dual pole. So in the single pole we have the single images like either HH or VV or HV or VH. Okay, so here we are transmitting H or V and receiving in H or V. So it will have a full swath. Okay, like from the design, and we cannot do the polarimetric decomposition with the single pole, because we have only single images, either HH, VV and HV, and it has the less hardware like IRS-12, radar set 1. Now dual pole have the, like, we are transmitting H or V and receiving H and V, means we are either transmitting H, then the combination is HH. If we transmit V, then VH and VV. Okay, so like that we will transmit one of the polarization and receive two of the polarization. So it also have the full swath, and dual polarimetric decomposition we can do because we have two images, and it has the moderate hardware. So we can have this Sentinel-1, Reset-1 and EOS-4 satellite as a dual pole. In the quad pole, we have transmit H and V and receive an H and V. So we have all four combination like HH, HV, VV and VH. So here it is VH. So actually it is the actually if we are using the all images, so with the compromisation of the swath. Okay, so we are dividing the beam at like a two beam, then we are compromising with the half swath, and it is a fully polarimetric, and we can do the fully polarimetric decompositions, and more hardware is required like radar set 2, pulsar, and EOS-4 has the quad pole and the hybrid dual pole. So this is the new concept in SAR polarimetry, in which we are designing the dual pole system with less hardware, but after the data processing we can get similar signatures like a quad pole. Means we are designing like a dual pole and we are having the quad pole type all the information. So in this, actually what we will do, we will transmit the circular polarization and receive H or V. So what the combination it can have, right circular, RH and RV, and LH and LV. This is the right circular and this is the left circular, and here also we are getting the full swath. So the with the compromisation of the half swath is fulfilled by the hybrid dual pole, and we can do the polarimetric decomposition also, and moderate hardware is required. Reset 1 and EOS-4 recently, which is Reset 1A, has the hybrid polarimetry also. So this is the SAR polarimetry, in which we have the full polarimetry. We have four images like HH, HV, VH and VV, and from there we will deduce different matrices, which is called the polarimetric matrices. So this is the difference between the horizontal and vertical polarization. So this is the horizontal polarization, so it will interact with the horizontal surfaces, and this is the vertical polarization, and it is enhancing the vertical structures. So now we will just see how scattering and polarization are related to each other. Okay, so earlier in my class, in the first class, I have told you the if we have the smooth surface, moderate and rough surface, then rough surface have high backscatter. Means if it is a single polarized, then we have, if it is a rough surface, then we have the high backscatter. Medium, it will have moderate rough surface have the medium backscatter, and the smooth surface has the very much low backscatter due to the specular reflection. So like lakes where the backscatter, which is very much smooth, okay, so this is actually exhibit the surface scattering. Okay, so the surface scattering occurs from the surface. Okay, like ocean surface, lakes, roads and bare surface. So one of the type of scattering is called the surface scattering. Next is the double bounce scattering. So what is the double bounce scattering? So in this double bounce scattering, if we have any building type structures, urban buildings, so you can see this signal is coming, hitting the building, and actually this building will help to backscatter the signal towards the radar sensor, and it is giving the very much strong return, because the this building the SAR pulses are interacting with this building and it is going back towards the sensor. So creates a very strong backscatter and appear as a very bright tone in SAR images. So the urban features have this type of properties of the corner reflector effect, which is called the double bounce scattering of a tall building. So we have like this, and the wave is coming here and it is coming here, and again it is going towards the sensor. So it is helping to scatter the signal towards the sensor. So that is called the double bounce scattering. So all these bright tones in the urban buildings you can see in the SAR image due to the double bounce scattering. Third is the volume scattering. So this volume scattering is actually given by the vegetation. So as you know, the tree has different components, like leaves have, it has the branches, it has the trunk. So the actually the SAR signal interacts with each of these signal. Okay, so what it will do, actually it is interacting, and actually it will have a multiple type of scattering. So each of the component will scatter the energy towards the sensor. And one more thing is the volume scattering is actually depolarize the signal. Depolarize means if we are sending the H polarization, then due to the multiple scattering by the different components of stems, leaves and branches, so the if we are sending the H polarization, then it will become a V polarization. Okay. So how this scattering and polarization is dependable. So we can say the magnitude of the polarization depends on the polarization state of the radar wave. Okay, for any surface the VV polarization response is greater or equal to the HS polarization. Okay, so if we are having the VV polarization, so VV is always have a higher backscatter or equal to HS polarization. HV will have a very lesser backscatter in any type of feature. The magnitude of scattering also depend on the polarization state relative to the orientation of the dominant scatterers. Means if we are as I told you, like how the backscatter is responsible. So backscatter is responsible by the target parameter and the sensor parameter. In the sensor parameter, the polarization also affect the backscatter. How it will affect means if the it is oriented in the horizontal or vertical direction. So in the HS polarization, the if the scatterer is along the horizontal plane, then we are seeing the more backscatter, and in if the scatterer is in the vertical position, we have the more polarization in the VV polarization. So if we can say, like if it is a like a ocean surface, then if there are waves are there, so it is becoming a capillary waves type of thing, then the V component actually is increasing in the ocean surface. So the if wind is blowing, then ocean surface enhances the wind will enhances the VV polarization in the ocean surface. So the ocean surface will look like a brighter tone. Okay, so the specular reflection will not happen, and in the VV polarization and the waves are there, then this due to these waves it will appear as a bright tone in the ocean surface also. So normally you can see this is the backscatter coefficient values, and this is the incident angle. So from here from incidence angle, low incidence angle to high incidence angle, we can see the backscatter is decreasing, and in different polarization the VV polarization is higher as compared to HH and VV. So VH. So VH and HV both have the lesser polarization as compared to HH or VV. So VV has the highest polarization value for a particular target. If we have a particular target and we have the four values HH, VH and VV, then in the VV it will be appear as a larger backscatter value as compared to HH and HV. So what is the depolarization? The volume scattering will cause the depolarization of the SAR signal. Vegetation will change the polarization state of the SAR signal. So H, if we are sending the H polarization, then the vegetation will depolarize the signal, and it will make the V polarization. Okay, so if we design the polarization like HV polarization, like if we are sending H and receiving V, then the vegetation in the HV polarization image will have the higher backscatter. Okay, so HV polarization image is basically used to identify the vegetation in the SAR image. So you can see there is a three images, one is HH and VV and HV. So in this case you can see in the HH and VV, so this ocean surface is appearing rougher as compared to HS polarization, because due to this the vertical component of the ocean surface is becoming enhancing in the VV polarization due to the winds, and this it has the vegetation. Here in the HH and VV it is same, and in the VV it is somewhat larger, and actually here you can see this is the buildings area. So this building area always have the corner reflector effect in every polarization, in this and in this. But if you can say relative feature discrimination, so in HV polarization, because this vegetation is depolarizing the signal, so in VV and HS the backscatter is very much lower because it is depolarizing here. But in the HV polarization, because we are sending H and the vegetation has makes the polarization and V, and we are receiving as V only, so we can see vegetation have the higher backscatter and it is mixing with the buildings. So this is the difference between the all three polarization, how the orientation affects the, and the volume scattering is affects the backscatter in the SAR image. So for the single polarization, if you can see, this is some structure. So in this structure you can say in the blue dots it has the vertical component and it has the horizontal component. So here in this orientation it has higher horizontal component and lower vertical component, and here the horizontal component is higher and vertical component is smaller. So you can see this due to the orientation, and we can divide the thing in H and V. We can see how much is the orientation in the horizontal direction and in the vertical direction, and accordingly in the SAR image the backscatter is there. Okay, so if we will we can have the SAR image. So if it is like this orientation, it will appear higher in the HS polarization. Okay, and if it has this orientation, then it is appearing higher backscatter in the VV image. Okay, so that is the effect of the orientation of the different feature in the SAR image. Now how the phase is actually comes in the picture of the polarization. So what is the phase? Actually phase is a measure of how far the wave has traveled. So if like wave is traveling one cycle 0 to 2 pi, 2 cycle 2 to 4 pi, 6 pi, up to the 3 cycles 6 pi. So if we are having different cycles, so means we can deduce like how much far has wave has been traveled. So the phase can be thought as a time for radar signal to travel from the antenna, scattered from some target and return to the antenna. Then these phase delays are introduced during the scattering process. Okay, like if it is interacting with the different Earth surface targets, and it will cause the phase delays. And depend on the scattering process, phase delays are introduced and measured by the radar. Okay, so this when this actually SAR signal we are sending, so it will actually do the scattering, and this scattering process will introduce the phase delay, and radar will actually measure that phase delay. So we can have multiple channels like HH, VV, VH and VV, and we can deduce the relative phase between them. and from there in the polarimetric analysis we can find out the interchannel phase difference for deducing the what type of the target it is. So the phase difference of 180 degree is completely out of phase, and phase difference of 0 degree is completely in phase. Without phase there is no polarimetry. So for doing the polarimetry we require the phase information. So we cannot do the image with the amplitude or detected image. We have to use the SLC image for the polarimetry. So we have one theory based on the scattering of different scatterers. So scatterers of simple geometrical structure creates a phase difference between HH and VV polarization by number of bounces or reflection that the radar signal experiences. The relative phase change by the 180 degree by each bounce. So when the signal is bouncing, okay, so if it is a surface scattering there will be no bounce, simple radar is interacting and it is going back, okay, so there will be no phase change. But in the dihedral effect corner reflector, like I have told you about this type of thing, double bounce scattering, so what it will do, it will actually it will change the phase with each bounce, it will change the phase. So it will have a even bounce. We have the dihedral corner reflector will exhibit the even bounce like buildings, okay, and here actually it is a single bounce, okay, and in the volume scattering it will depolarize the signal, okay, so it is the volume scattering is happening, so full H polarization is becoming the V polarization. So like a copole like HH and VV, it will have the odd or even bounce. So we can make out the odd and even means if they are in phase, then they are in phase, then we can say they are in the odd bounce. Then if they are in out of phase, then we can say it is an even bounce. So what we can do, like in the point and pure targets and distributed targets. So how we can define the point target and the distributed targets? So if we have a very strong target like a building where the area is smaller than the range resolution cell, means if any target which is having a very much small area and it is coming under the resolution cell, okay, so it will dominate the full resolution cell. So of all the backscatter information will come from that point target only. Means if there is a like a corner reflector is there in the resolution cell, so if the size is smaller than the resolution cell, then all the backscatter information will come due to that one target only, so it will dominate the resolution cell. So these type of targets is called the point targets. So like all main targets like building, power lines are considered as the point target. Now second is the distributed target, like if the target having larger area than the resolution cell, means like a natural surface, all the natural surfaces are considered as a distributed target. So in that type of thing, in within a resolution cell, all the scatterer will combine into one backscatter value, so that is coming under the distributed target. Okay, so we based on the pure or point target and distributed target, we have different mechanism to decompose our polarimetry image. Okay, so one is the scattering matrix. What is the scattering matrix? Now I have already told, we in the SAR polarimetry we have the four images like HH, HV and VH and VV. So if we will put in this fashion in the matrix form, then this is called the scattering matrix and it is called the 2 by 2 matrix. So scattering matrix is generally used for the pure targets. Okay, so if we are considering the if we are doing any application for the analysis of any buildings type structures and the urban things, then we can use the scattering matrix. Means if we are analyzing the point targets, then we can use this type of matrix for our polarimetric application. Next is the covariance matrix. So where we have to use the covariance matrix? So covariance matrix actually used for the distributed targets. Okay, so distributed targets means our scattering matrix, we can vectorize it. We have four components: HH, HV, VH and VV. So assuming like HH, HV and VH is same, like a monostatic case. Monostatic means if we have the same transmitter and receiver and the same at the same platform of the satellite, then there is a monostatic. Bistatic means if it is in the other platform, means in the transmitter and receiver. Most of the satellite have the monostatic in nature, like transmitter and receiver in the same satellite. So we can consider the HV is equals to VH, and we can vectorize this one like this, HH, HV and VV. Okay, and we can do this multiplication like this vector into the complex conjugate of the this one. So if we multiply like this, then we are getting the, this is 3 cross 1 and this is 1 cross 3, then we can get a 3 cross 3 matrix. So this covariance matrix, and another is coherency matrix. This coherency matrix is also used for the distributed targets only. So in this actually we can make the vectorize like HS plus VV, HS minus VV and HV. So like HS plus VV, what we are doing, we are just adding. So here actually what we are doing, it is representing a odd bounce. Okay, because they are in the phase, so we are having the odd bounce. In HS minus SV, actually it will represent an even bounce, because for the even bounce the phase is difference. Okay, there will be a one bounce more, so there is a phase difference between the HH and VV polarization. So if we subtract this one, so we can get a response for the even bounce. So that is the odd bounce and this is the even bounce, and this is the HV is the volume scattering. So we have vectorized like this, and again what we are doing, just we are doing the matrix multiplication of these vectors and getting the 3 cross 3 matrix. So if you want to analyze on the point targets, then only singular matrix or scattering matrix is sufficient. And if we want to do the analysis on the distributed targets, then we have to use the covariance and coherency matrix. So why these matrices are actually needed? So actually these are needed for our polarimetric decomposition. Now what is the polarimetric decomposition? The objective of the polarimetric decomposition is to express the average scattering mechanism as the sum of the independent elements to associate a physical mechanism to each element. Like if this is the singular scattering matrix, so what we will do, we will make 3 matrices. Okay, 3 scattering matrices of individual elements. Like if say if we want to deduce as 3 type of targets. One target is like it should be a odd bounce, second target it is of even bounce, and third is the volume scattering. Okay, so like surface scattering will given by the odd bounce, and the double bounce like buildings will give by the even bounce, and the vegetation type of thing is given by the volume scattering. So we will deduce this matrix as 3 elements. Okay, so this is the way we can decompose. Now it is the if we have different polarimetric decomposition, lot of literatures are there. So it depends on your analysis with how you can decompose. So every type of decomposition will do this one, means it will reduce as a 3 component, 4 component. Okay, so different type of targets orientations. So we can make a different polarimetric decompositions and for our study. So I will explain a single thing here. So based on the like target characteristics, we have the two type of decomposition, like coherent decomposition and incoherent decomposition. So what is the coherent decomposition? If we want to study the pure target or point targets where the resolution cell is dominated by a particular target, then we have the coherent decomposition. Okay, now what is the incoherent decomposition? If we want to study the distributed targets where the resolution cell is dominated by each distributed scatterer, then we can use the incoherent decomposition. So we have the coherent and incoherent decomposition. In the coherent decomposition, we have the poly decomposition, Kroeger decomposition, Cameroon decomposition, and incoherent are the Freeman, Hinan, and the HA alpha and Yamaguchi decomposition. So we have different decompositions. So what this decomposition will do? So I will explain taking one as an example, like a poly decomposition. So what is the poly decomposition? So the poly decomposition express the scattering matrix as a poly basis. Okay, so what it will do? So this is the actually the scattering matrix for the for the trihedral or a odd bounce. Okay, here or surface scattering we can say. For the surface scattering, like a ocean surface or a river body or the open fields, there will be a odd bounce. Okay, so now odd bounce we will say means if we have the odd bounce or 3 bounce or 5 bounce, so they will have the same characteristics. Okay, like a odd bounce, like if we have a 1 bounce, 3 bounce, 5 bounce, that is a odd bounce. So it can be a trihedral, or if we have the any surface have 5 planes that actually have the same property. Dihedral means they are like a double bounce targets. So here we can see 1 minus 1. So I already told the scattering matrix like HH, HV, HV and VV. Here what we can do, like here actually the phase is not changing. So surface scattering I have said like with between the HH and VV there is no phase change, so it is same 1 1. In the double bounce there is a phase change, so 1, and there will be a negative value. And in the volume scattering we have the actually depolarize the signal, so it has the in the HV polarization we have the 1 value. So this is HV polarization, it is depolarizing, so we are putting a 1 1 value here. So that is a scattering matrix for the volume scattering. So this is the scattering matrix of the single bounce, that is for the double bounce, and that is for the volume scattering. Now for the decomposition what we will do, this is the matrix, and we will decompose in this term like first matrix, second matrix, and third matrix. We will do linear combination of this one, and we will put some coefficients like alpha, beta and gamma, and putting this value here, and from this we can deduce this coefficient in the form of HH and HV. Okay, so after doing some calculation, we can find out alpha like this one, HH plus VV under root 2, and beta is this one, and gamma like this one. So if we have, like now we have decomposed this matrix as a 3 component. Okay, 1 component, 2 component, and 3 component. Now if we are getting any SAR image, and we have the full we should have a fully polarimetric SAR. So if we have the HH, VV and HV polarization, so we can make these 3 coefficients and we can put in the RGB scale. Okay, so we will put R for the even bounce, and B for the out bounce, and green for the volume scattering. As the vegetation is green, so we are putting the vegetation as a green. Even bounce like a building structures where the dihedral properties are there, corner reflectors, so it will come as a even bounce. Odd bounce means surface scattering like a open surface, river bodies, that will come as a blue. Okay, so we are putting these things as a thing. So you can see this is the year 4 quad pole data of Dehradun region only. So it is the HS polarization. So after doing the poly decomposition, so you can see it has the different colors. So it will actually this red color will have the point target analysis. So I have already told, like, poly decomposition is good for the point target analysis. Means if it is good for the like a building structures, and that one it is coming good. For the distributed target, we can apply further, like a Yamaguchi is there, H alpha decomposition is there, so that classification we can do. But for the example point of view, we have taken like a EOS4 image and the poly decomposed image. So what we have done, just we have calculated these three terms and we have put up in the RGB scale, so you can have a colorful image of the SAR using the SAR polarimetry, and like a multispectral image we are using the optical. So SAR polarimetry is will give the color images in the SAR. So because we have the multiple bands here in this one, so we can do the classification also using different classification techniques of the polarimetry also. So this is the one image of the Dehradun area. So you can see this is the same FRI image which I have showed you in the first lecture. So you can see this is the building of the FRI. So it is appearing as a double bounce. Okay, so you can see this red things all are double bounce, and vegetation green is coming as a vegetation. So in this image you can see this is the FRI building, so it is coming as a double bounce characteristics. So double bounce I already told you, that is having the corner reflector effect, and it will come as a red in the image. Now we will go to the another concept of the hybrid polarimetry. So EOS4 has all these four combination, like it can have a single polarimetry also, dual polarimetry also, quad polarimetry also, and the hybrid polarimetry also. So up to this term I have told you about the linear polarimetry. Linear polarimetry means there is the HH, HV, VH and VV. In the four components are available. So we have the four combination HH, HV, VH and VV. From there we can deduce the polarimetric decomposition image, and again we can do, after this we can do the classification also on this decomposed image. Now second important thing is the hybrid polarimetry in the EOS4. So what is the hybrid polarimetry? So objective of the hybrid polarimetry, I have already told you, like quad pole data actually will reduce the swath, and its hardware is very much costly, and it has the volume data also, because we have four images and it is in the float data, so that is very much high data is there. And transmit power, actually it is required more in the quad polarization, because we have to generate four images. So what is the solution in the, actually if we have the dual polarization, then dual polarization has actually the full swath, and the transmitted power requirement are also less, and we have the data volume also is less, because the it is a half of data volume. So hybrid polarimetry is evolved, in which what we have done, we are transmitting as a circular polarization and receiving as a linear polarization. Means if we are transmitting as a right circular and receiving as a HV, then we have two image, RH and RV. So if we have this hybrid polarimetry, then there actually has the Stokes vector. So we can directly deduce this Stokes vector from the hybrid polarimetry, and this Stokes vector is basically we will make some different decomposition, which is special class of decomposition for the hybrid polarimetry, which is M delta decomposition and M chi decomposition, which is similar to the our full pole decomposition. Okay, so M delta is actually comparable with the Freeman decomposition, and it can apply to the distributed targets also. So the hybrid polarimetry is actually design like it is a dual pole polarimetry, but it is actually giving the images have the property like a full pole polarimetry. So in the circular or hybrid polarimetry, it is utilizes the degree of polarization and relative phase, which can be estimated through the Stokes vector. So these are the Stokes vector. From there we can deduce the degree of polarization and relative phase, and we can put up this thing in this fashion, and like S0 is the Stokes vector, and m is the relative degree of polarization, and delta is the relative phase, and we can deduce into three components like odd bounce, even bounce, and volume scattering. So we can make like a weighting function of the sine function. Okay, so 1 plus delta, so I already told that is plus we are using for the same phase, and minus is using for because that even bounds are out of phase, so we are using 1 minus sine delta, and here we are using degree of polarization as a in the FV, because we know the volume scattering, what it will do, it will depolarize the signal, so we are doing 1 minus m here. So this is the special m delta decomposition, and we can make a color image out of it from the two images itself. So if we can take the raw data or SLC data from the image, and we can do the if we have directly the SLC data, we can go by the SLC data. If we have the raw data, then we can process the raw data and make the SLC, and then we can do the Stokes vector and then m delta decomposition and make the colorful image in the hybrid polarimetry. So you can see this is the Mumbai area of the EOS4 image. So this is the RS mode, like right circular horizontal mode, and this is the EOS m delta decomposed product. So it is actually like similar, only like it will have the green as a vegetation and the blue as the odd bounce, and the red as a even bounce. So you can see in this area, so you can see in this image, this is the some bridge is there. So in this bridge you can see this is the bridge, and this it is coming as a red things. So it is actually the pillars of the bridge actually. Okay, so that is coming like a standing objects, so that is coming like a double bounce criteria, and these are the vegetation, and this is the urban buildings using giving the different colors based on their scattering properties. Okay, so in the polarimetry, either it is in the fully polarimetry or it is in the hybrid polarimetry, we have to do some type of speckle filtering. So in these images we have not applied any speckle filtering on. Okay, so we have special class of speckle filters. So already I have told you what is the speckle. Speckle is the actually the noise which is generated through the constructive and destructive interference of the signal, and where it is the constructive interference, it will be having the bright, and if it is a destructive interference, it will be have a dark energy. It is a random phenomena, so it is producing a random black and white pixels in the SAR image. So we have the speckle filters. Good speckle filter is like it should preserve the edges, means like a building structures, it will not do the smoothing, and it should do in the uniform regions like a water body. It should remove the noise, and it should not have any artifacts, and radiometry should not change, like a dB value if it is there, so it should not change that dB value. So multi-looking is one of the form of doing the speckle filtering and making the square pixel size. So the process of multi-looking improve the SAR image by quality by reducing the speckle, and allow us to obtain a square pixel on the output image, either in the range or azimuth direction, or in the both direction. We can average the signal. So what is the multi-looking? We can actually sum the signal. Okay, so as you know that averaging always increases the signal, either in the optical or SAR image. If you average any pixels, and if it is a noise, so if we do averaging by taking 3x3 kernel or 5x5 kernel, so it will be a low pass filter only, and it will remove the noise. So in the multi-looking case, already I told, like a SLC, we have the range resolution and azimuth resolution are different, and it is not a square pixel size, there is a rectangular pixel size. So what we will do, we will make a square pixel size by doing the multi-looking, means we will do the averaging either in the azimuth direction or range direction, or either in the both direction. So for example, if the resolution in azimuth and range direction of the SAR are 5 and 20, like it is a 5 meter in the azimuth and 20 meter in the range, then image can be multi-look 4 times in the azimuth, so that the size of the each pixels becomes the 20 by 20. Okay, so what we will do, we will take the 4 pixels and we can do the averaging type of thing. So that type of thing we can do in the multi-looking. So in the multi-looking, what we can do, so here you can see this is the actually the image. So after doing the multi-looking, you can see the in the water body the noise is reduced somewhat by just averaging the things, and the ground pixel size is also become like a square pixel size. Then there you can see the compression is there. Now the geometry of the SAR is also somewhat improved. Apart from simple multi-looking, we can have a special type of speckle filters. So it can have like a non-adaptive filters and the adaptive filters. So what are the non-adaptive filters? And actually the parameters of the whole image are considered in the non-adaptive filters. Like if we are having the image, so it is doing the denoising on a full image. Okay, so it is a global type of algorithm, like a FFT algorithm. What is the FFT? Like if we will take the frequency domain, we will take the Fourier transform. So in the Fourier transform, it will decompose the image in the high frequency and the low frequency, and as you know, the noise is a high frequency, and so we can use the low pass filter. So it will actually attenuate the high pass frequencies, and then we can take again the IIFT, inverse FFT, to convert back to the time domain. So that is the non-adaptive, means it is taking a full image, doing the FFT and removing the noise and coming back to the time domain. Now in the adaptive filters, what are the adaptive? It is taking like a small windows. Okay, so for a particular image, we will choose one small kernel, and for that small kernel, like if we are doing, so we will make one 3x3 5x5 kernel, and for that 5x5 kernel we will find out some local statistics. Okay, local statistics means mean and sigma. So for that local statistics means for a particular target, and we can have a particular small region of 3x3 or 5x5. We will calculate the mu and sigma for that one, and that is used to remove the noise. So we have different adaptive filters like Lee, Kuan, Gamma Map. So they are adaptive, means it is calculating the mu and sigma local statistics from the image itself. Why it is calculating the local statistics? Because as you know, the statistics, if we are calculating the mean, so mean is actually the signal in the image, and the standard deviation is the noise in the image. So for each pixel for a particular region, we can calculate the mu and sigma, and we can find out the what are the different parameters, and based on that parameters we can have different filters like Lee, Kuan, Gamma Map are some of the adaptive filter, and this actually you can see the effects. So Gamma Map and Kuan is better filter and remove the noise better in a better way. Nowadays these are some of the classical filters. Nowadays new filters, edge preserving filters are also come, so we can use that filters also, like a wavelet filter. So that filters can also be used to reduce the noise from the SAR image. So we can see some of the images of the EOS 4 of the full polarimetry. So this is the Dehradun region. So you can see in this image, this is the water body, it is coming as a blue, and you can see some urban targets which is appearing as a pink. Okay, and the vegetation, it is coming as a blue. So if we have not applied any speckle filter, so the image can be made better by removing the noise. Okay, so we have just done the decomposition based on the single look image only. So this is, you can see this is the image, it is the single bounce, it is there, and it is showing the volume bounce, and this is showing the double bounce. And here you can see the corresponding optical image. So it is not of same time period, but approximate we can see. So you can see here this is vegetation, and that is the buildings are there. Okay, so and this vegetation that is coming as a green one only. So you can just correlate the our structures with the optical image also. So here also you can see one image. So here these things, it is coming blue as an open field, so that is open field, and where the vegetation is there, so it is coming as a green one, of volume scattering is there, and some of the high rise building, it is coming very much point target of red, it is coming as a double bounce. And this is the, actually you can see the Kankaria Lake of the Ahmedabad full polarimetry product. So you can see this is the thing. There you can see the double bounce, and there is also a single bounce. So it can be some structures are there which is showing the odd bounce type of thing, and there is a double bounce. Here you can see this is the M delta decomposition hybrid polarimetry product of the US4. So you can see this is the images. So you can see in the optical you cannot see this point things. It is almost same resolution, but you can see this point, it is coming as a double bounce things like these points. Okay, so these are actually the electric poles. So in this is like this thing, it is a ground range ground photograph actually. So this is actually from Google Street View. We have I have just seen that what are these marks. So this is coming like a electric poles, some marks are coming. So here you can see this is the Mumbai area only, and this is the under construction bridge which is connecting the Navi Mumbai and our Mumbai, and that one. So here you can see this is the small point are the actually the pillars of the bridge. It is coming at a final. In this is a Ahmedabad image. Sorry, it is a Kolkata image, and it is the actually the stadium, Eden Garden Stadium. It is appearing in the SAR image. So in SAR we can have different exploitation also. So what we can do the object detection, we can do the maritime application like ship detection and monitoring, we can do the oil spill detection, bathymetry we can do, change detection we can do, and data fusion, SAR and optical, flood mapping we can do, and we can do the object height, some rough height we can do, and we can do the soil moisture analysis. And if you are having two applications like SAR polarimetry and interferometry, here actually we can do with the single pole data also, this type of thing. But if we have the phase data also, so we can do the SAR polarimetry and SAR interferometry. So in the SAR polarimetry we can do the decomposition, signature analysis, and the classification we can do, and interferometry which I will cover later. So we can do the across interferometry, angle on track interferometry, differential polarimetric in SAR. So that things we can do. So like oil slick detection, we can see this is the input SAR image, and we have detected this oil slick, and with this detection we have just created the mask of the oil slick. By automatic detection, what we can do, we can just find out how much spread is there, we can find out the area of the oil spill, because this oil spill is actually a specular reflection in the ocean, and if the ocean is having the wind also, so it will appear more bright, more contrast, means more darker region. So we can deduce easily in from the SAR image having the some windy climate, and oil slick is there. This is the ship detection we can do. So as I told you, like ships are the bright targets, and it is over the ocean surface, so that is almost a black. So we can have different algorithms, CFR based algorithm. So we can detect automatically the ships, because once we are just see also, but automatically detection is very much useful for the operational purpose, because we cannot do everything manually. Like oil slip, we cannot do the manually digitizing the thing and we can calculate. If we are able to do the automation, means directly we can do, then we can calculate the area, and here we can calculate the ships. So it is the ships, it is the Suez Canal, and during the stuck of Suez Canal some ships are there. So that is the near the Suez Canal. So we can do the change detection type of thing also. So you can see this is the old image of Hyderabad around 2020. It is a flood time. So you can see in this is of 9th October 2020, and this is 21st October 2020, Osman Sagar in the Hyderabad. So how the it is detection has been, how much change has been happen in the lake, and if we are able to deduce the water body extraction, so we can just extract the water body from here and water body from here, and we can do the comparative analysis. We can do some mensuration like height of the object. So as the formula is h cot theta, and if we can see, if there is an image and there is an electric pole, and you can see that is a layover. So if you are having this type of thing, like it is an homogeneous space and some alone target is there, so at that time we can find out the layover, and based on this layover we can find out with the help of the incident angle how much is the height. But it is very much difficult if it is in the like a city, because there is lot of urban targets and layover is happening here and there. So if it is a homogeneous region and isolated targets are there having some height, there we can do some rough estimate of the target using the formula. So we can do the SAR polarimetry. Already I have told you about the SAR polarimetry application, and we can do the optical fusion, SAR and optical fusion also. So you can see this is the optical image, SAR image, and this is the optical image, and we have just fused this image to image just for our interpretation, because we are more habitual of the optical image. So if we have the SAR information like backscatter information of any particle of any target and optical spectral signatures also there, then we can fuse it and we can deduce some more feature extraction from the image. Okay, so so I will stop this lecture of SAR polarimetry, in which I have told you about the SAR polarimetry and some of the image exploitation. There is lot of application of the SAR, so we cannot cover each and every topic. So some of the things which we have done in our end, we have shown you. So that are we have different application in every field, like water resources we have different application, geology we have different, agriculture we have different, urban we have different, disaster we have the different applications. So every field have different application in the SAR imagery. Okay, so SAR imagery have the complementary information as respect to the optical imagery, and because it has the amplitude image, it has 24/7 coverage, it can penetrate through the clouds, and more powerful technique, it has the phase information. So phase information we can deduce the polarimetry and interferometry, and do the different target signature analysis based on the polarimetry. And interferometry is used basically for the surface deformation and generation of depth, which I will cover after